So notice that an identity matrix is in reduced row echelon form. Further, if A is a square matrix of order n with row entries, then the matrix A is either row equivalent to the identity matrix of order n, or is row equivalent to a matrix B, which is also a square matrix of order n with row entries, with one or more rows that consist entirely of zeros. So we can use this fact to prove a theorem. So let A be a square matrix of order n. Then the matrix A is invertible if and only if the square matrix A is row equivalent to the identity matrix of order n. So proof. Suppose that the matrix A is invertible and assume to the contrary that A is not row equivalent to the identity matrix of order n, then the matrix A is row equivalent to a matrix B with one or more rows consisting entirely of zeros. Now, since matrix A is invertible, and the matrix A is row equivalent to the matrix B, then the matrix B is also invertible. But this is a contradiction. Since any square matrix with a row of zeros is singular. And hence, by contradiction, the matrix A is row equivalent to the identity matrix of order n. So conversely, Suppose that the square matrix A is row equivalent to the identity of order n. Then there exist elementary matrices E sub 1 through E sub k such that the matrix A is equal to the product of these elementary matrices and the identity. And of course, this is equal to the product of the elementary matrices. Now, since each elementary matrix is invertible, the product of the elementary matrices, which is the matrix A, is invertible. So notice that by the previous theorem, if the matrix A is invertible, then the matrix A is equal to the product of elementary matrices with the identity. Further, the inverse of A is the product of the inverses in reverse order. The identity is its own inverse. And since the identity commutes with any other element, we have the product of the inverses of the elementary matrices in reverse order times the identity. Also notice that A inverse times A is the identity, and this is the product of the inverses of the elementary matrices in reverse order, which is the A inverse times A gives the identity. That is the same sequence of elementary row operations that reduces the matrix A to the identity will transform the identity to the inverse of A. So this gives us an algorithm to find the inverse of an invertible matrix. And we call this the inversion algorithm. So to find the inverse of an invertible matrix, which we call A, we find a sequence of elementary row operations that reduces the matrix A to the inverse, or correction, to the identity of order n, and then apply this same sequence of operations to the identity to obtain the inverse of A. Now in practice, we can accomplish both simultaneously. By adjoining the identity to the right of the matrix A. That is, we form a larger matrix. We have the matrix A together with the identity to its right, and we transform the matrix A to the identity and thereby transform the identity to the inverse of A. So notice that to apply the inversion algorithm, we assume that a square matrix is invertible, and if during the process of reducing the matrix A to the identity, we obtain a matrix with one or more rows consisting entirely of zeros, we have discovered that the matrix A is singular. So let's look at an example. So let A be the 3 by 3 matrix with rows 1, 0, 1, 0, 1, 1, 1, 1, 0. We will use the inversion algorithm to find the inverse of A if it exists. So we adjoin to the matrix A the identity Now in row 1 we have a leading 1, and so in that column we need to have zeros elsewhere. And so we will add to row 3 -1 times row 1. And so row 1 and row 2 remain unchanged. Now -1 plus 1 is 0. 0 plus 1 is 1. -1 plus 0 is -1. -1 plus 0 is -1. 0 plus 0 is 0, and 0 plus 1 is 1. So now in row 2 we have a leading 1, and so we need to eliminate the 1 in row 3 that is in the same column. So now we will add -1 times row 2 to row 3. So again, row 1 and row 2 do not change. -1 plus 1 is 0. -1 plus -1 is -2. 0 plus -1 is -1. -1 plus 0 is -1. And 0 plus 1 is 1. So now in row 3 we need to have a leading 1, and so we will multiply row 3 by negative 1/2. So again, row 1 and row 2 do not change. Now for row 3, we have 0, 0, 1, 1/2, 1/2, negative 1/2. Now in row 3, we have a leading 1, and so we need to eliminate the 1 in row 1 and also the 1 in row 2. And so we will multiply row 3 by negative 1 and add this to row 1. So row 2 and row 3 do not change. Zero plus 1 is 1. 0 plus 0 is 0. Negative 1 plus 1 is 0. Negative 1/2 plus 1 is 1/2. Negative 1/2 plus 0 is negative 1/2. And 1/2 plus 0 is 1/2. And so now we need to eliminate the 1 in row 2. And so we will add to row 2 negative 1 times row 3. So row 1 and row 3 do not change. Negative 1 plus 1 is 0. Negative 1/2 plus 0 is negative 1/2. Negative 1/2 plus 1 is 1/2. And 1/2 plus 0 is 1/2. So now on the right-hand side of this larger matrix, we have the inverse of A. So A inverse is the 3 by 3 matrix with rows, 1/2, negative 1/2, 1/2, negative 1/2, 1/2, 1/2, 1/2, 1/2, negative 1/2. And so this is the scalar multiple 1/2 times the 3 by 3 matrix with rows 1, negative 1, 1, negative 1, 1, 1, and 1, 1, negative 1. So as an exercise, let A be the 3 by 3 matrix with rows 1, 2, 3, 2, 5, 3, 1, 0, 8. Use the inversion algorithm to find the inverse of A if it exists. Okay, so we will end here for today. Next time we will look at transposes of matrices and an introduction to determinants. So I hope you have enjoyed the 9th lecture. Thanks for watching.